In the last 2-3 videos, we talked about the notion of irreducible elements and prime elements in an arbitrary integral domain, and we also introduced the notion of greatest common divisor for a pair of elements, and we saw an example where the greatest common divisor may not exist. So the general statements we have proved, let me quickly recall without writing them. We proved that in any integral domain, a prime element is irreducible. That's automatically true, but irreducible elements may not be prime. And we saw an example of the ring Z adjoint square root of -5, in which case, in which ring 2 is an irreducible element, but it's not a prime element. So in the next couple of videos, we are going to study two very important classes of rings in which irreducible elements are in fact going to be prime. Okay, and the first class of examples is class of rings are called principal ideal domains. Okay, so they are referred to in short as PIDs. So principal ideal domains are very simple. So a ring, so this is the definition, an integral domain R is called, so I will always use the abbreviation PID for principal ideal domain. So an integral domain is called a PID if as the name suggests, every ideal must be principal. Every ideal of R is principal. So in other words, every ideal I is in fact generated by a single element. So the most important examples that we have encountered already in the course are of course the ring of integers and the polynomial ring in one variable over a field, right? So these are some of the standard examples, and of course K, a field itself. A field is definitely a PID because it's an integral domain and it has only two ideals, the zero ideal and the unit ideal, both of which are principal. So we have three examples here. This second and third are in fact classes of examples. And some other rings that we have encountered before which happen to be PID is this. Okay, so this I will not prove for you because that will take me away from what I want to do, but the idea is the same as the examples we have considered. So if you quickly recall, how did we prove that every ideal in Z is principal or that every ideal in Kx is principal? We used essentially what is called Euclidean algorithm, right? Euclidean division algorithm. We have the notion of size in these rings. Size of an integer is just its absolute value. Size of a polynomial is its degree. So given any ideal, we picked an element with the least degree in the polynomial ring and least positive number in the case of integers. Here we have a size given by the norm of an element of this. So as I said, I won't go into details, but we can always do the following. Given an ideal, we can pick an element with the least possible norm or size, which is the sum of squares of the real and imaginary parts. So this is the size of A plus IB, and carry out the same procedure that we used. Given any ideal, if it is zero ideal, we are done. If it's not, pick an element with the smallest size. Then argue that every other element is a multiple of this by sort of dividing the two elements. So we can carry out the division process exactly as in the case of integers or in the polynomial ring. But this is a useful example of principal ideal domain. What is not an example of principal ideal domain? And it is this, some familiar ring to us. It's a very nice ring otherwise, but this is not a PID. The reason is the ideal, for example 2, x is not principal. It's not difficult to check this explicitly, right? Because if 2x is principal, say what is a principal ideal? It is generated by a single element. So say it is generated by a polynomial fx. Then first of all you argue that f must not be a constant polynomial. In other words, degree of f must be positive. Why? Because I will just say this and I will let you work out the details. If degree of x is 0, that means fx is actually an integer. It's a constant polynomial, means it's an integer. No way that it can generate x, because remember, if 2 comma x is equal to fx, x is a multiple of fx, so it cannot be a generator. It can't be an integer because x is never a multiple of an integer, unless it's 1, of course. But if it's 1, the ideal generated by 1 is the entire ring, which 2x is not. So degree of fx must be positive, and once it's positive, 2 is not a multiple of . Because if it's a positive degree polynomial, when you multiply by any other polynomial, degree only increases. It may stay the same if you multiply by constants, or it will actually increase if you multiply by non-constant polynomials, but it will never decrease. So you can never obtain 2 as a multiple of this. Okay, this is a simple explanation for why Zx is not a PID. Similarly, Kx1 xn is not a PID if n is at least 2. Right? The reason is the ideal x1 comma x2 is not principal. The same kind of reason as before. These are two independent variables, so you cannot choose any single polynomial whose multiples are x1 and x2. So this will never happen. Okay, if you remember the language of irreducible elements, x1 and x2 are irreducible elements, so they cannot be written as products, multiples of some other polynomial. Same polynomial will not do for x1 and x2. x1 of course is a multiple of x1 and x2 is a multiple of x2, but there is no single polynomial whose multiples include x1 and x2. So these are not PIDs. So these are nice rings, polynomial rings over in n variables over a field where n is at least 2, and polynomial ring in one variable over the integers are nice rings, but they are not PIDs. Okay, so what are some interesting properties of PIDs that I want to emphasize in this video? So properties of PIDs. Properties of PIDs. One is that these are actually propositions. Proposition, let R be a PID, then any irreducible element in R is prime. Remember that we saw in an example that in general, if you have an integral domain, irreducible elements may not be prime. Though prime elements are always irreducible, but irreducible elements are not necessarily prime in general. However, in a PID that happens to be the case. Okay, so actually I should make this proposition 2, and I will write proposition 1 first now, which I will prove first, and then we will do proposition 2. Okay, so what is proposition 2? Let R, proposition 1, what is proposition 1? Let R be a PID, and let us take two elements, then A and B have a GCD. Okay, so I am going to use this to prove the second proposition. So this, why is this? I want to say that if you have two elements, then GCD always exists. As I have again indicated in the same example, R equal to Z adjoint square root minus 5, this is not generally true. So let me recall, this is not in general true, as the example of edge . So I don't remember the two examples, maybe this. So you take these two elements, they are both elements of the ring R, they are not units, and they have no greatest common divisor. So however, in the case of PIDs, any two elements have GCD. And why is that? So let us consider, it's very simple. Both propositions are in fact very easy to prove. So let I be the ideal generated by AB. ideal generated by A and B. Since R is a PID, I is principal. Every ideal is principal. So let I be equal to some D for some, it's a principal ideal, so it is generated by a single element. Let's call that D. Then we claim that, as you guess, D is a GCD of AB. Remember, GCD, there may exist several GCDs, but D is one of them. So first of all, remember what is GCD? We have to show one, that D divides A and D divides B. So let's quickly check this. Why is this true? Remember, the ideal generated by AB is equal to the ideal generated by D. But A is an element of the ideal generated by AB, so A is an element of the ideal generated by D. That means A is equal to dx for some x. Similarly, B is an element of AB, so B is an element of the ideal generated by D, so B is dy for some y, which is exactly the definition of D dividing B and D dividing A. So D divides A and D divides B. In other words, it's a common divisor. Now we need to show that it is a greatest common divisor. So let us choose E, an element of R, let E divide both A and B. Right? So let E divide both A and B. That means, then I claim that A, B, the ideal is contained in E. Why is this? This is because Ax equal to E, By equal to E for some x and y in R by definition of E dividing both A and B. That means Ax, sorry, this is not correct. I should write Ex equal to A, Ey equal to B. E divides A, that means Ex is equal to A for some x, Ey is equal to B for some y. That means A is of the form Ex means A is in Ex. A is in the ideal generated by A. E. Similarly, B is in the ideal generated by E. So AB is the entire ideal. If the generators are in some ideal, the entire ideal generated by A and B is in E. But this is actually DE. So that means the ideal generated by D is contained in the ideal generated by E. That means the element D is in the ideal generated by E. That means D is equal to Ez for some Z. Right? D is an element of E means D is an element of the ideal generated by E means D is of the form E times some other ring element. That means E divides D. So this completes the proof of the proposition which said that any two elements have GCD. Now I am going to prove the second proposition. So this is proof of proposition 1. Now I will do proof of proposition 2. Remember, proposition 2 said in a PID every irreducible element is prime. So let A in R be irreducible. Right? So suppose we want to prove that A is prime. Right? I claim that every irreducible element is prime. So we want to prove that A is prime. But if prime means, so suppose that A divides a product of two elements, let's say BC, where B and C are in R. So we want to show that A divides either B or A divides C. Okay, so now assume also that and A does not divide B. If it divides B, we are done. Suppose it does not divide B, we are going to show that A divides C. Okay, so now note that, so by proposition 1, there is a GCD of B and A and B. Remember, when I write GCD of A and B, it may suggest that there is a unique GCD, but I am not claiming that. This is just a convenient notation for me. All I am saying is that there is a GCD which I am calling D. Let us take the GCD of A and B. Now we know that D divides, by definition of GCD, D divides A. So D divides A, but A is irreducible, right? By hypothesis, A is irreducible. So we have two possibilities. An irreducible element cannot have proper divisors. So either we have that D is a unit, or D is an associate of A. Right? We have that D is an associate of A or D is a unit. Because A is irreducible, D is not, because A is irreducible, A cannot have proper divisors. D is a divisor, it cannot be proper. So in other words, it fails to be proper either because it's a unit or because it's an associate of A. I claim that the second case cannot occur, because if D is remember that A does not divide B, right? I am assuming that A does not divide B, but D divides B. So D divides B because D is a GCD of A and B, so definitely D divides B. So now D divides B, A does not divide B. So A and B cannot be associates. Remember, what is the meaning of associates? They either differ by a unit, or in other words, D is a multiple of A and a unit, or equivalently D divides A and A divides D. So if D divides B and A divides B, A does not divide B, A cannot divide D, because if A divides D, then if A divides D and D divides B, that means A divides B, which cannot happen. So in other words, D and A cannot be associates. So this case cannot occur, right? I'll put it like that. This case cannot occur. So D must be a unit. So D is a unit. But this means the ideal generated by D is entire R, because a unit is an element which has a multiplicative inverse. That means D times some element is 1. That means 1 is in the ideal generated by D. In other words, it is equal to R. But that means the ideal generated by A and B is 1. Right? Because D is the GCD of A and B. That means the ideal generated by AB, by previous proposition. How do you get the GCD? It is the generator of the ideal generated by A and B, which is R. So ideal generated by A and B is R. That means there exist elements R comma S in capital R such that RA plus SB is equal to 1. Right? Because 1 is an element of R. 1 is an element of R. It is also simultaneously an element of the ideal generated by A and B. Any arbitrary element of the ideal generated by A and B is of the form RA plus SB, where R and S are two ring elements. But that means I can multiply both sides by C to get RAC plus SBC is equal to C. I am just simply multiplying this equation by C. So RAC plus SBC is equal to C. But now note that this term A divides this term by definition, right? Because it is A times RC. On the other hand, A also divides this term. Why is this? Because A divides BC by hypothesis. A divides BC, so A divides SBC. No matter what S is, A divides SBC. This means A divides C, right? Because if A divides RAC, A divides SBC, that means A divides their sum. If two elements are divisible by A, their sum is also divisible by A. So A divides C, which is what we required. Right? So this completes the proof of the proposition. The proposition claimed that any irreducible element is prime. So if you have a PID, every irreducible element is prime. I have just proved that. I have started with an irreducible element which divides a product and it does not divide one of them, and I have concluded that it divides the other. So this finishes the proof of proposition 2. Some other properties of PIDs is that a PID is Noetherian. This is very easy, right? This is a one-line proof. every ideal of a PID is principal. So certainly it is finitely generated. Right? It's much stronger in fact than being finitely generated. So PID is automatically Noetherian. And one final proposition I will do just to illustrate some interesting properties of PIDs. Let R be a PID. Let capital P be a non-zero prime ideal of R. Then P is in fact a maximal ideal. P is maximal. So in a PID, it's an interesting statement that, which is in general certainly not true, every non-zero prime ideal is maximal in fact. So let's prove this. So since P is principal, the property of a PID that every ideal is principal is extremely powerful, as these propositions are telling you. So since P is principal, we have a generator A, let's say, for some A non-zero. Remember, that is because P is non-zero. P is non-zero means P is not the zero ideal. That means it has non-zero elements. So it is generated by a non-zero element. Now I want to show that P is maximal. What is a maximal ideal? It's an ideal which is not contained in any bigger proper ideal. So we are going to take a bigger ideal. Let I be an ideal of R such that P is contained in I and I is contained in R. Of course, I is contained in R, but the point is it contains P. So again, using the hypothesis that I is principal or R is PID, I is principal. So suppose I is generated by a single element, right? So what we have is just rewriting this. A is contained in ideal generated by A is contained in the ideal generated by B. So A is an element of A which is contained in B. So that means A is an element of the ideal generated by B. That means A is equal to BC for some C in R. By definition, A is a multiple of B. So A is equal to BC for some C in R. Hence, A equal to BC belongs to P. And P is a prime ideal. Remember from a few lectures ago, what is a prime ideal? It's an ideal such that if a product belongs to that ideal, one of the elements belongs to the ideal. So B is in P or C is in P. So let us see both implications. Both cases give us something, right? So suppose B is in P. In this case, the entire ideal B is contained in P. That means, of course, we know that P is contained in B by hypothesis. That means B is equal to P. So this is okay. I am trying to prove that there is no bigger ideal. In this case, it just happens to be the same ideal. Suppose B is not in P. Okay, then what do we have here? So C is in P, right? Because remember, either B is in P or C is in P. Because P is a prime ideal. If B is not in P, C is in P. So, and what is P? P is the ideal generated by A. So, C can be written as AD for some D in R. For some D in R. But now let's start with this earlier equation. A is equal to BC. So A is equal to BC, but C we just observed is AD. So this is BAD. That means A is equal to BAD. That means A times 1 minus BD is equal to 0. I am just subtracting BCD from both sides, BAD from both sides and factoring A. But since B is non-zero, A is non-zero and R is an integral domain, one minus BD is 0, right? we have in an integral domain, if two elements multiply to 0, one of them must be 0. So that means B is a unit, right? That means B is a unit because BD is equal to 1. So B has a multiplicative inverse. So B is a unit, and hence the ideal generated by B, which I called I, is R. Okay, so we are done because I have started with an arbitrary ideal that contains P, and I have concluded it's either equal to P, or it's equal to R. Okay, so P must be maximal. It's an interesting statement that every non-zero prime is maximal. So again, we see that by in this example. So this is not a PID as I proved earlier, and in this there are the ideal P, which is generated by 2, is prime, non-zero, but P is not maximal, right? Because P, which is generated by 2, is contained in 2x, right? So this is not equal to 2 and this is not equal to zx. So again, this is not maximal because it's contained in a proper bigger ideal. So this again confirms that Zx is not a PID, because in a PID we have shown that every non-zero prime ideal is maximal. Okay, so these are some of the properties of PIDs, and in the future videos we will talk more about this. So just to recap what we have done, PIDs are rings where every every ideal is principal. The most standard examples for us are integers, polynomial rings over any field, and fields of course. But some of the other nice rings that we have considered, ZX, polynomial rings in more than 2 variables, are not PIDs. PIDs have the nice property that any irreducible element is prime, and they are Noetherian. Any 2 elements have GCDs, and every non-zero prime ideal is principal. So let me stop this video here. In this video we have talked about principal ideal domains. In the next video we will start learning about unique factorization domains. Thank you.